stuff that the stuff that you need to get done but don't really want to get done.
Yeah.
But it's so much easier. I have faith that I will survive the series. I'll be dead by the end of it.
Yeah.
Hmm.
Yeah, that makes it better.
I should clock that 5 minutes that I spent. I can't. I'm projected. I can't. Until tomorrow. I can add it tomorrow. So, are we trudging knee deep into stoichiometry today?
We need to go back, and I forgot to do the oxidation stuff.
Oh, Marissa, how could you do this? That's why I struggled with it on the homework.
Yeah, because we didn't cover it because I forgot about it. I didn't really forget. We just had like one day for lecture.
Yeah. So much freaking math.
Math is good for you.
Math is going to end up killing me. I couldn't find 5 in my stash, so I just printed a new one and did it.
Cool.
And the copper lip pad will get finished, hopefully.
What are you even doing?
Hopefully the rest of your class does.
I think I have your email because I sent you that article.
Hmm?
The rest of your class is still missing. Only 6 minutes to go.
That's been a theme this term. A lot of people showing up right at time or late.
atoms towards you, and then like the dashed line showed with. What do you do for double bonds? How do you show those double bonds, like spatially? Is there a way to do that?
No. But you might not necessarily want to, because maybe it doesn't have like 3D structure anymore.
Okay.
Yeah.
I'm just curious. Question I wrote down.
Yeah, because usually kind of like breaks 3D-ish. Oh. I forgot.
I guess nobody's found a class today.
Yeah, I know we have 2 minutes. One person is online, so thank you. And if you're online, please say hi. We'll give everybody 2 more minutes.
Oh, your stool's gone.
I know, I didn't put my stool out.
Thank you.
Your table.
Yeah. It's not enough surface area.
How did your leg not fall asleep doing that?
I don't know.
I
I'm
could
used
never.
to 5 feet tall, makes you compay.
The perks of being tiny.
Yeah. Like, every seat has extra leg room in the airplane for me.
Yeah, I used to be a twig. I used to be very small like a twig. I think back in high school I was just cresting through 9. And then I grew, and it was painful.
Morning.
What's up?
How's the lab?
All right, we're at official class time. So a couple of announcements before we begin, of course. Just a reminder, we have our extra credit opportunity this Friday, so you can thank, again, Tony for doing that. And so I actually have a flyer pulled up today, so you've probably seen it posted. And so it's Joan Reed here, a family nurse practitioner, and went to school locally in Oregon as well as going down to SoCal. So you can, again, attend that talk for 5 bonus points on your exam. And as I mentioned on Tuesday, I'll be ensuring that it is live streamed. So if you can't make it live or can't watch it at that time, you have work, other obligations, you can catch it later. All right, any questions before we kind of get started? I realized that I forgot some things since we were so pressured last week. So I wanted to go back and touch on the oxidation reduction section and just go over that, and then we'll hit some other questions about polarity, and then hopefully some molarity or moles practice stoichiometry. All right, so going back to our redox. So again, right, our redox reactions involve an exchange of electrons. And so either, right, usually we have a free element going into an ion or vice versa. And so if you have a free element going into an ion, right, that's going to be a metal going to a metal plus. And so typically the metal is going to be losing electrons, right? So your metal is always losing electrons, again, based off of your metallic state, and then going off to a compound. And then, of course, if something loses them, another must accept them. So again, generally like the right side of our periodic table, kind of our nonmetals, right? So I'll say like nonmetals are what tend to accept them. So again, you can refer to your periodic table that reminds you of their typical oxidation states. And then, so a couple of reminders here. So atoms that lose electrons that means that they are oxidized. And later we'll learn this also means that they are the reducing agent. So again, the thing that is supplying electrons. And then atoms that gain electrons are being reduced. And so that is a reduction reaction, sometimes referred to as the oxidizing agent. Yeah.
Does this mean that redox reactions can only happen with ionic pairs or with ionic compounds? And like that would be something to look for on a test if you're trying to identify a redox reaction, is if it's ionic or not?
Yeah, so then you're looking for something, like in this case, we have something in its metallic form and then going to its ionic form, and then vice versa, right? So again, elemental form to ionic form. So yeah, that would be a good clue. So if you see something in the elemental form and it's going ionic, or vice versa, right? Ionic back to elemental. So yeah, that's generally a good hint that it's a reduction reaction. And I'll write our little mnemonic too, so you can remember. So I have two different mnemonics depending on how you feel. So I'll do the first one. So I was born in Texas originally, and so of course we love oil there. So hence where this one comes from. So oxidation is losing electrons, and reduction is gaining electrons. And of course, some people may have feelings about the fossil fuel industry, or maybe you just don't like oil rigs, but instead like cute little tigers or leopards or whatever you want to call them, lions. So I used to work at an institution where the mascot was a leopard, so we used to say Leo the leopard goes grr. You can make it the lion or whatever your favorite cat is, but losing electrons is oxidation, and gaining electrons is reduction. So those are good things, right, to write at the top of your paper or your cheat sheet or your exam. And so then we want to practice how to identify redox reactions. Again, right, good hints there that we're looking for something elemental form, not elemental, or vice versa. So that's always a good hint. But let's look at our kind of rules. So let's skip down to our rules. And so let's look at this caveat first before we kind of dive into it. And so it depends what we're like looking at specifically. So this statement, let's just read it. So it says chemists assign a number to each element in a reaction called the oxidation state. And so that allows us to determine the flow of electrons. And so then it makes this statement that oxidation states are not ion charges. And so sometimes it is the same, right? So it depends if we're looking at like an ionic compound, and then, right, those oxidation states tend to track with their ion charges. But later we'll kind of revisit this. But we also just have oxidation states as a formality to track electrons as it states. And so we'll kind of revisit this idea, like third quarter, we'll look at organic structures and kind of look at oxidation states in a more formal setting and kind of more mathematical. And so that's what that means. So sometimes it is measurable, again, if we are looking at an ionic compound, and then we can measure that charge. Otherwise, it's electronic bookkeeping, essentially. And so then we have these kind of rules. And again, it reminds us that these ions in an ionic compound are measurable charges versus, again, the formality of maybe a molecule. All right, so these are our rules. So the number one rule is that your free element, so again, something in its elemental form by itself, has an oxidation state of 0. So again, just how it's found in nature by itself. So sodium, right, as a metal. Diatomic chlorine has an oxidation state of 0. All your other diatomics, so that's 0. Okay, good starting point. And then our monoatomic ions have an oxidation state equal to their charge. And so, right, I would prioritize that, which I believe. So this gives us, right, our priority. So meaning fluorine is always -1, and then base hydrogen off of 1+, oxygen is generally -2. Then the rest of group 7s with -1, group 6 with -2, group 5 with -3. And then like we've kind of seen, so again, the oxidation state will be equal to the charge. And then the sum of the oxidation states, if it's a neutral compound, will equal to 0. Or, of course, if it was charged, then it should equal the charge. All right, so then let's look at some of these and how to assign our oxidation state. And so now we're looking at our polyatomic ion nitrate here and how to assign it. And so again, oxygen would take priority. So oxygen, -2, and then we have an overall -1 charge. They set up the algebra for us. So -2 times 3 is -6. And then, right, so you have -6 plus x equals -1. So then x equals 5. So, right, base nitrogen off of oxygen is what that means. So nitrogen can have, right, different oxidation states. So this is also an example of kind of our formality too, and just bookkeeping and showing, right, that nitrogen is donating its electrons there. And then, just as we expect, our group 1 metals have our oxidation state of 1+, group 2 are 2+, and then again we have this priority here. So let's look at a few exceptions. So we can have this class of compounds. And so we have this H here that's bound to a metal. And so this is called a hydride species, sometimes referred to as like H- formally. And so this is, again, right, electronic bookkeeping. So our hydrides have a -1 charge when they are bound to metal. So, right, so anytime you see hydrogen bound to metal, it's likely a hydride with -1. So you can have, right, like iron hydrides as well. So iron dihydride and others. And so again, hydrogen takes a -1 oxidation state here, and then that would leave aluminum as 3+, which is what we would expect there. And then other exceptions, and so again, oxygen is almost always -2. The only exception would be peroxides. So peroxides take this general form, so we can look at hydrogen peroxide. So that's hydrogen peroxide, so it's the simplest peroxide. But any peroxide just has this sort of structure where R represents any organic group. So this could even be like nitrogen technically. Not sure how you would synthesize that, but it does exist. But anytime you see oxygen bound together with a single bond, this is your peroxide group here. And your whole peroxide group has a -2 charge, so generally you see it represented like so on a polyatomic sheet or other reference. And so if you notice, well, there's 2 oxygens with the overall -2 charge, so that means that each oxygen is -1 for those peroxides. So just keep that in mind. So, right, anytime you see peroxide, a little alarm bell should go off, and oh, okay, that's different, and that's the only time oxygen is -1. But otherwise, base everything off of oxygen being -2 to solve things, especially, right, those polyatomics, or like in this case, we're looking at CO2. So again, -2 for our oxidation state for oxygen, leaving carbon as +4 there. And so now I'll go back to our example at the top here, and we can identify things. So take a second. I'll have you try it first. So look at this reaction. So sodium plus sulfur gives us sodium sulfide. So see if you can identify first the oxidation states, and then who's getting oxidized, who's getting reduced, right? Who's our reducing agent, who's our oxidizing agent. And then I am keeping an eye on the chat. So again, if you're there, say hi, say your answers. I can't respond back for some reason on this computer, but all right, so tell me oxidation states here. So what's our oxidation state of sodium? Oh, but it's in, what do you notice about sodium? What form is it in? So yeah, see a 0, right? Because it's in its elemental form. So it's not bound to anything. It also gives us a hint, right? It's a solid. So we know sodium's a metal solid. So good. 0 by itself. What about sulfur here? What's its oxidation state? Also 0. Excellent. Elemental form. And then just as a note, so people are inconsistent with how they show sulfur. So just always keep an eye on this in your reaction, right? So they have reported sulfur as just S, but more correctly, sulfur is found as S8. So depending on who you're looking at, sometimes people show S8 there, and then you'd be 1/8 of S8, right? So just something to keep in mind, so don't get confused by that. But they didn't show that. Again, it doesn't really matter too much. And so then it reacts. So now what's our oxidation state of sodium in our compound? Say it louder. What does your periodic table say? +1, right? So it's group 1. It should always be +1. So write like a giant 1+ over on your periodic table if you haven't already. And then, so what's sulfur? So -2. All right, good. So now we can do our analysis, right? So sodium went from 0 to 1+. So did it gain or lose an electron? I think somebody said loss. Let's say it loud, right? So it lost an electron. It got more positive. And then we want to kind of do our electronic bookkeeping with this. So we'll get into balancing redox reactions a little later, more formally. But you do at least kind of want to keep an eye on your electrons, right? So of course we have 1 electron movement, right, for 1 sodium, but then we have 2 equivalents, so we're losing 1 electron but then times 2 for sodium, so right, 2 electrons there. Now let's examine sulfur. So did sulfur gain or lose electrons? So gain, right, it became more negative, and then in this case it did gain 2 electrons. And so good, right? So we had to have 2 equivalents of sodium to supply those 2 electrons to sulfur then, so that all balances out, right, by charges and by electrons. So good there. And so now we can say, so who was reduced? So sulfur, excellent. And so who got oxidized? So sodium. And then other terms, because again, a working chemist will likely be interested in trying to test different reducing agents. So what's your reducing agent in this case? So sodium, excellent. Again, it is the workhorse supplying those electrons. And then that leaves our oxidizing agent as which one again? Sulfur, excellent. So just, again, getting the hang of those terminologies. And now we're appreciating, thinking back to safety, like way in the beginning when we mentioned the oxidizing agent. It has like that little flame with the circle, right? So that's just telling you that it kind of has that additional hazard of being an oxidizing agent. So, right, again, it's ready to accept those electrons, which can potentially make it more reactive. All right, let's repeat that process with this one. So again, do a little analysis. What are your beginning oxidation states? What are they in the product? Who's doing what? All right, so walk me through this analysis. So what's my oxidation state of iron in the beginning here? 0, so excellent. Again, elemental form. And then what about oxygen? So, yep, 0 again. So right, diatomic elemental form, so good. And then it reacts to make iron oxide. And so let's start with oxygen, since that one is consistent. So what's oxygen? So -2, and so what does that make our iron in this case? So +3. So excellent. So again, just kind of doing our electronic bookkeeping. So we're seeing each iron, right, loses, so -3 electrons. But then there's 4 equivalents, so times 4, so 12 electrons total in that process. Now let's look at oxygen. And so again, gaining 2 electrons individually, and then there's 6 of them. So 12 electrons again involved in that process, so that looks good, right? We should be exchanging the same number of electrons. All right, any questions about redox stuff? I know it's kind of fast, but at least I think that's enough to help you with the homework and kind of get through everything. Unless there are any other like burning questions that came up. All right, let's shift gears for a second. So now I wanted to mention a few things about polarity. Yeah, we'll do it here. Because, again, I forgot to mention polarity. And so let's look at what makes something polar or non-polar. And let's take a few examples for a second. So let's compare methane versus carbon tetrachloride versus, so this is dichloromethane, and we'll stop there, also known as DCM or methylene chloride. Although I think this is now becoming a more regulated substance for fun. Well, I'll let you analyze that and then I'll give some fun facts. And so what do we think about these? So let's just start with methane. So what do you think about methane? Is it polar? Is it non-polar? How do we determine that?
Slightly? Is there a difference between electronegativity is 4 or 5? There'd be more electrons than protons?
So, I mean, maybe, right? There is a slight difference in polarity, but then what about the shape of the molecule and our vectors?
It is completely surrounded, so they kind of cancel out, right?
Yeah. And so this is, so I'll pull back up the chart. And so this could be hard to see. You know, again, we're in Gen Chem right now. If you can train your brain to think in 3D at all times with chemistry, like you'll do wonderfully, especially in OChem. But this is hard to do. Like, I can't understate this enough, right? Like, it's okay if you're not here. And so then what we want to do is kind of use this as a guide. And so what I always tell people, because like, yes, if you're in physics too and you're like really good with vectors, like that's what we're essentially trying to do, is like we're looking at our pull of our electrons and we can write out our vectors. Although for this case, I would still say this is pretty non-polar of a bond, our CH. So let's look at carbon tetrachloride then, right? So we'll fully establish why this is non-polar in a second. But let's look at carbon tetrachloride, right? So this is maybe trickier. So we have this carbon-chlorine bond, and right, we might say that this is polar. And so I'm going to draw out the vectors though. So how we think about it is, again, right, where it's pulling. And I believe this is opposite convention from physics, and kind of drawing in bad 3D right now. And so in chemistry, we want to show where the electrons are being pulled. So the arrow kind of goes towards a more negative region. And then I like to think our little plus sign arrow, I put like the plus sign to show, okay, this is positive. So, right, again, electron density being pulled outward. But yeah, it's being pulled evenly in all four directions. So again, if you're kind of more physics-minded in physics dealing with vectors, this might come more easily to see this. Otherwise, I like this guide, and I might like highlight this, but everything in the first column here would be considered fully symmetric, because what you're essentially looking for in determining whether something is polar or nonpolar is there a break in symmetry, right? And so in this case, it's fully symmetric. And again, it's easier if we kind of look at this compound chem sheet when we're first learning. And so, okay, it's based off of our 4-electron pair tetrahedral. And so if all these elements are the same, or like roughly the same electronegativity, then it would be considered nonpolar. So yeah, methane is nonpolar. And then that would mean that carbon tetrachloride itself is also nonpolar. Since even though these are, again, individually polar bonds, it cancels out in the other directions. So then what about dichloromethane? So polar, nonpolar?
Polar.
So polar, right? I think people were saying it. So say it loud, say it proud. So yeah, polar. And now we can tell that it's polar. I mean, you could also draw, right, your vectors that it's going to be kind of pulling more towards the chlorine side with this one, since chlorine's more electronegative. And so we could think about, again, its electrostatic density map. We can also see, again, it breaks the symmetry. So now you have 2 hydrogens and 2 chlorines there. So that creates unevenness and, again, breaks our symmetry. That being said, it can be difficult to determine polarity. Yeah, question?
Comment, actually. I kind of thought about it the way that we think about water. I looked at the chlorines and they're negative. I looked at the hydrogens and they're positive, so they pull away from each other. That's how I pictured it.
Yeah, that's perfect. Like, and then that's good too. Like trying to see analogous structures or anything, right? Like, water kind of looks like that with the lone pairs, and that gives it polarity. So again, anytime you have either electronegative substituents or if you have lone pairs themselves, yes, we have a break in symmetry and also polarity. But so I'll bring up a few issues with the homework. So for instance, CO came up again on your homework, right? And so we had established in class that that was a weird one. And so if you remember from class, we had established that the formal charge ended up being negative on the carbon, which was unusual, positive on the oxygen. And I did say that this was consistent, right, with experimental results that showed the carbon attaching to the metal. Well, if you looked at my answer key and perhaps asked the internet, you might find all sorts of discrepancies about whether CO is polar or not. And so admittedly, I didn't write the key. I just kind of stole it, and then I always forget to change it every year. But it's a good opportunity too to talk about the correct answer. And it's again, I'm not so focused on the correct answer, but what does the experimental data show? And so let's look at that, because that's really what we should be referencing. And so if we look at CO, oh geez. And so, okay, well, how do we solve this, right, other than watching people argue on the internet? And so we have a measure for this. And so the value that you'd actually want to look at if you're trying to get a true sense of, again, how does it behave, is the dipole moment. Now, unfortunately for you guys, we don't have a good context yet of the dipole moment, so let's kind of look at a few things. So you'll have to take me at my word right now and just say this is a pretty low dipole moment, so that means it's essentially nonpolar. And so again, our dipole moment tells us how polar it is. I pulled up a few examples, again, so you could put yourself in context. So methane, right, you all have predicted that it's nonpolar. And so if we go down to its dipole moment, it has a perfectly zero dipole moment. So yes, it is completely nonpolar. Then if we look at carbon tetrachloride, let's look at the same thing. Also, fun fact, so this is, now I might talk some gibberish. So carbon tetrachloride used to be used a lot. So it was actually used as an NMR solvent because if you look at it, it has no hydrogens on it. And so a proton NMR works by giving you a pretty picture of all the hydrogens in your molecule, essentially. So you can't put it in a competing solvent, right? So what I'm saying is, like, you can't have your molecule, you can't dissolve it in benzene, that's just like regular benzene, because then all you'll see is a giant benzene. And so before they moved over to deuterated solvents, so now deuterated meaning that you use heavy hydrogen, so this would be deuterated benzene, such that it does not give you a signal. It still gives you a minus signal from the impurities. You tend to buy this in like 99% purity. Anyways, so this was used, no hydrogens, no signal. So it's a great solvent, except it's now been pretty much phased out due to extreme toxicity. So I have used it personally, but again, it's fallen extremely out of favor. It used to be like the solvent, but it's toxic. And so let's go down to its magnetic moment, or dipole moment. And so once again, 0, so perfectly nonpolar. And then let's look up, I didn't have a chance to pull up dichloromethane. Oh, I got distracted by other stuff, by dichloromethane. So dichloromethane is, I would call it the workhorse solvent of an organic chemist. Let's do some fun facts about DCM. So this is what DCM looks like. Let's verify that it's polar. So there's the dipole moment, so 1.6. So again, giving you a context, right? So now getting more polar. Let's look at water. Again, just to give you some context. Oh, geez. So water is going to be pretty polar, so let's find its dipole moment. So 1.8 there for water, right? So again, getting higher with its polarity, just putting it in context. All right, fun facts about DCM though. So I don't know, again, what your chemical career will look like. So like I said, this is a workhorse solvent. Here's the problem with DCM. So I would not consider myself a workhorse organic chemist. I'm an organic metallic chemist by training. That said, so a lot of my coworkers that are organic chemists use a lot of DCM for columns and extractions and everything. The problem is you get this phenomenon known as the DCM burn, we'll call it. So if you were to ever get DCM onto your hands, well, it goes through your glove immediately, and you will feel it because it burns. It gives a weird burn. And so you immediately want to change your glove, and I've experienced that before. But like I said, my coworkers, more workhorse organic chemists that are out there in the fume hoods running columns, you eventually develop some sort of weird sensitivity towards DCM, where even the fumes can like make your hand hurt after prolonged exposure. So this was a pretty recent development. This is still controversial. I'm actually not sure how a lot of laboratories are handling this, because I think this was, when did they do it? So yeah, this is all recent, like 2004, 2005. They're now trying to manage the risks now from DCM. And it's in a lot of things, obviously. So it's just a very common solvent. But yeah, just not to go down the rabbit hole, but this is a huge issue for both research chemists, of course, because research chemists use this on a small scale. But like I mentioned, there are still grad students that were probably getting overexposed to DCM. But so that's that. And then, yeah, do we see? So that's why CO, like I said, is not really polar, but you might expect discrepancies. Oh, and then other oddities. So you had, I believe, SO3, right, as your Lewis dot structure. And I believe that one also said that it was polar, but I would disagree with that. And again, right, if you look at it, so looking at it, and so this kind of comes into your question maybe about double bonds. So once you start getting double bonds, right, the structure though is planar. So that's the important thing to keep in mind, is like, when is it 3D, when is it planar? So now this is planar, right? It's trigonal planar. So if we draw out our vector structure, right, it's all even in 3 directions. We could also go back to our compound chem here. So right, it's like trigonal planar, again, fully symmetric. So SO3, right, I would expect it to be nonpolar based off of our Lewis dot structure. And then, like I said, it's always good if we're confused, right? You can read all sorts of junk on the internet, but we can always look up its dipole moment. Okay, now let's look up its dipole moment. Wikipedia let me down. Is that, I just wanted to know that that was a measured value. Oh, that's irritating. All right, eventually, maybe I'll look at the NIST or something. I just wanted to make sure that that was a true calculation of a dipole moment of 0, but. All right, let's see if we can do some stoichiometry now. So let's just try to go, oh, this is not the right note, sorry. Let's go through this. Have I already told you about the Haber guy, right? I feel like I have. Yeah, pretty important dude. All right, so start with this quiz that this isn't our current quiz. This is just a quiz that I've given in the past at other institutions, and people didn't do very well. So I thought we'll do it together as a warm-up. So we're going through our stoichiometry. So we're given our balanced equation. So again, that's always the first thing we should check. Is our equation balanced? And so this is kind of, I would say, our setup, our warm-up, right? Putting us in the right frame of mind. So just kind of go through these questions really quickly. So what's our molecular weight of hydrogen, molecular weight of diatomic nitrogen, and then ammonia? So what do we get for our molecular weight of H2? 2.016, so grams per mole. What about nitrogen? 28.014 grams per mole. And I see that in the chat as well. Excellent. And then last one, ammonia. What do we get for that one? 17.031 grams per mole. Wait, what do we get for this? 17 point?
031. Should be 031.
031. Okay, just making sure. All right, excellent. And so, right, if you're on an exam and you're completely lost, this is always a good first place to start with, right? Just find your molecular weights of everything so that you have your gram per mole amount. So that kind of helps figure out what's going on. All right, so now let's, again, think back to your friendly s'mores for these. So now, if we have 4 moles of H2, how many moles of nitrogen do we need to react? I'm trying to show everything. I can rewrite this equation larger. Should hopefully have this written. That's right. Think about what we're doing, what conversion factor may be. Again, it was kind of easy with the s'mores, but so what do we need to do, right? So essentially, we want to make our conversion factor. And so maybe, right, just do that before you start to try to get an answer. So just look at your equation. So you're comparing H2 and N2. So you can essentially set up your relationship. So for every 1 mole of N2, you have 3 H2. Then we can just set up our dimensional analysis. So if we have 4 moles of H2, and then it works out, I happen to write it correctly. So, right, H2 will go on bottom, N2 on top. Otherwise, right, you can just flip this conversion factor. And so you should get 4/3, or I see the answer in the chat, 1.33 moles of N2. Does that make sense to everybody? Do we all get 1.33? So then try that again. So now if we have 2 moles of N2, how many moles of ammonia will we produce? So right, what is it asking you to compare? Set up your dimensional analysis here. So again, I would look at our conversion factor. So our relationship, so for every 1 mole of nitrogen, we create 2 of ammonia. And so then what's our answer then if we have 2 moles of nitrogen? How many moles of ammonia? So 4. Okay, excellent. Does that make sense? Tracking so far? And so again, right, we can always compare our mole-mole ratio with our balanced equation. All right, so now let's try 6 and 7. So 6, 7, and 8 are all related, so we'll kind of tackle those. So if we have 20 grams of nitrogen, how many moles of hydrogen do you need to react? And if we have 20 grams of hydrogen, how many moles of N2 do we need? So see if you can solve that. How would you approach it? So what do we get for 6? Kind of walk me through it. So what do we need to do first?
Convert to moles.
So convert to moles, excellent. So 20 grams, and then, right, that's what I was saying. If you're ever lost, it's always good to kind of give yourself this. So now we can just look at what we calculated. Okay, perfect, 28.014 grams per mole. And then, so then we could just set up, right, so this will give us moles of N2. And then we could use, right, our mole-mole ratio. Again, they're in a 1:3 ratio. So now I'll put for every 1 mole of N2, we need 3 of H2. And so what does that come out to? So let me I'll pull up my calculator. You guys can yell at me. So 2.14, and chat agrees, and I can quickly punch that in. So 20 divided by 28 times 3. So good, and I believe you reported it to the correct sig fix, so 2.14 moles of H2. And then repeat that process. So now how many moles of nitrogen is needed to react? So again, same process. Now I'm dividing by my mass of hydrogen, so 2.016. So this gives me moles of hydrogen. So then I'll use my conversion factor. So still 1:3 ratio. But now we'll divide, right? So for every 3 moles of H2, we need 1 of N2. So then what do we get for that one? So how many moles? So 3.31 And Chet agrees, so moles of H2. And so now looking at these, so 20 grams of nitrogen and 20 grams of hydrogen, so which is the limiting reagent? And so there's different ways to go about this, right? But you can maybe go back to the mole ratio and figure out how many moles of product. That's probably the most straightforward way. So which one is our limiting reagent? So nitrogen, excellent. And then, so how did you come to that determination?
Because you have only 0.71 moles of nitrogen, but almost 10 moles of nitrogen, 20 grams.
Excellent. So that's good. So I like what you did, right? Just go back, compare the original amounts. Again, use your mole ratio, right, to figure out how much product you can make. And again, it's N2 for this one. All right, so then now, given our limiting reagent, how many grams of ammonia should be produced? And I'll just start kind of sketching it out. So kind of recalculating moles, or you could have started with the 0.71, and then going back to our equation here. So 1:2 ratio. So for every 1 mole of nitrogen, we get 2 of ammonia. And then it asks for it in grams, though, so then times 17 grams per mole. So 20 divided by 28. So times 2 times 17. So about 24.3 grams of product. And so then the last step here, I think we've kind of practiced this in lab, but it's good to practice it again. And we'll just kind of go over, right, how to calculate this formally. And so again, right, this is more relevant when we're in a laboratory setting, and then you want to figure out, like, how much do you have in your hand? That was the whole point of the copper reaction. And so your actual yield is, again, right, what you did in lab. So I always say, like, right in your hand, what you're holding. And then the theoretical yield is always, right, what we calculate with stoichiometry. And so again, that's always, right, what we predict. So if we go back to this little mock quiz here, so, right, this would be our theoretical yield. That means 100% yield, everything went perfectly fine. The reaction went to completion, and then we didn't trip and lose half of our product on the floor or anything like that. And so let's see what our percent yield for this reaction is. So it looks pretty bad. So what we actually had minus or divided by what we expected. So what's our percent yield for this reaction? So 17%, so this would be a pretty abysmal yield. So 17.3, I'll give it 3 sig figs. So hopefully that's not your yield. That being said, so just kind of giving context to things. So if you were an organic chemist, so an organic chemist typically wants their reaction to be greater than 90% yield. You can probably guess as to why. So these organic chemists, especially a good hardcore synthetic organic chemist, like maybe doing natural product synthesis, you're going to have like a 20 to 30 step synthesis. And so, right, just take that 0.9 to the power of 30. That gets really small really quickly, right, for their overall yield. So they really want to maximize every step. And I've heard plenty of horror stories of, right, your natural product synthesis chemists, they lose their product, you know, step 29 in the water bath down the sink. So I've heard of some interesting extraction methods to try to get their product back out. So, and then that being said, a metallation reaction, those tend to be dirtier, so sometimes those can be acceptable to like 50%. So, and that's considered like a decent yield for a metallation. But again, just depends on what type of chemist you are, what you're trying to do. And then obviously if you were an industrial scale chemist, right, you'd be trying to get that as optimized as you can. All right, I think that's all the lecture part I had. I did have like an aside I wanted to mention. Yeah, so this always turns into drug the class, but I felt like it was super relevant with all this stuff that was going on in the news. And so this was, go away. So this is a new article that was just posted, and I thought it was fascinating from a chemical standpoint because this is what I don't understand about like drugs and laws and like how they come up with this. And so I don't know if y'all missed this or not, but they just passed a federal hemp ban, so they're trying to outlaw all the derivatives. And so as a chemist, like I have several different thoughts on this. Like, I'm surprised that a chemist hasn't gotten involved in the legislature and kind of defined more tightly what derivatives are allowed or not. And so I just kind of wanted to go over, again, just like briefly, because this is what is so hard about like drugs and trying to control drugs, but then also like what chemists do. And so, right, a good working chemist, and I'm just showing, right, CBD right now, since, again, all of the THCs. So all the cannabidiols, basically any derivative of this has been federally banned. And, again, as a chemist, like, it feels kind of confusing and frustrating. That's why I'm surprised that some patent lawyer chemist hasn't gotten involved and, like, defined what can and can't be changed legally at these different art groups. But just to kind of appreciate it, so this one is the acidic form, and I'm going to point out, so this is a carboxylic acid group, so that's what makes this acidic proton. And again, right, you're just like doing slight modifications to this molecule. And so different derivatives, different carbon chains, right, so this one is shorter on the carbon chain there. This one has an extra chain over there. Right, all this is to show you there's a ton of synthetic derivatives, right? And again, that's what a chemist can do, is a chemist will take a molecule, modify it. So you can make hundreds of derivatives. So that was part of the problem So like the delta 6, that's what they're after, right, is like, obviously the THC is illegal, but then people were trying to get around it with the delta 6 or delta 8 stuff. So I think it was the delta 8. Again, just like minor derivatives, right? So that's what a chemist does. You just take something, you derive it. So now they're trying to go completely illegal with everything. And again, I don't really comprehend it. That's my ask to you. You guys should be better legislatures and try to come up with drug rules that actually make sense. And to my point, so I wanted to point out the difference between cocaine and crack cocaine, because right, those have very different historical like treatments of how they were punished. But from a chemical standpoint, they're almost the same. So like, I really don't understand it. And yeah, I mean, a lot of it goes into kind of, I guess, socioeconomics of who are the actual drug users.
Is that benzene on the end there?
Yeah, why not? That's a typical organic molecule. So yeah, you gotta have some rings in there. That's pretty common. But yeah, so this is cocaine.
Oh, it's just working on identification.
Yeah, so good. So right, so we got our cocaine here. And so the difference between cocaine and crack cocaine is so cocaine is the molecule form, right? So again, thinking of what we learned, so okay, that's a molecule. And so this would be a drug that you could take. So I don't remember how, so cocaine, right, you can inject that directly. And then, so crack cocaine, right, is they say you gotta purify it. Again, I'm just talking about this theoretically. And so notice the difference is that it's in the salt form. So meaning it's been protonated. So then we made the hydrochloride salt is what it's generally known as. And so again, right, protonated there. Maybe it's easier. I was trying to find a good picture. So this nitrogen, again, it gets protonated, becomes positively charged, and then you have the counter ion of the chloride. And then, of course, if you're going to consume it, right, that's why they say react it with the base. So then you do, right, little acid-base reaction and convert it back to the molecule. So then, from a chemical standpoint, I do not understand why there's a difference then in the law and why I think historically crack got a much harsher sentence than cocaine. And they're literally one is the salt form and one is the molecule form. So again, from a chemical standpoint, I don't understand it. So there's that. And now we have THC as another issue. But, right, that being said, most people are completely chemically illiterate. That's why you guys are in here, right? I mean, people say all sorts of stupid stuff with chemicals, like, oh, there's chemicals in there. Water is a chemical. Sorry, people saying things are like chemical free is like my number one trigger, I think.
Did you know they put that hydrogen monoxide in the water fountain?
Yeah, you got to be careful with the dosage of dihydrogen monoxide. Everything will kill you, though, right? Dosage makes the poison. So, and well, we could go on, right? Like fentanyl. So fentanyl was made by a group of researchers at MIT. So they were trying to get something that would be more potent, right? And well, now we got fentanyl. So again, there's always two sides to everything. So drug development has a lot of politics in there. Anyways, probably done rambling and talking about how to do drugs. So now that I'm going to get reported, let's take our quiz. So I'll hand out your quiz. So it's a little longer today, so it covers a little bit of the ionic compounds. So right, again, open book. So get out whatever notes you need, reference other notes. So a good review of the past few chapters here. you. Everybody get a quiz? Everybody.
I forgot my backpack. Can I get an extra copy of the periodic table?
Oh, yeah. Let me get one.